No problem, children. I'm back this week with another one, and I hope y'all are enjoying the content I put out. If you are, please do me a huge favor. Hit that like button, smash that subscribe button, then comment down below to let me know how I'm doing. If y'all are really liking content, please share this with your friends and family. Today I will be covering FTT122 Assignment 6. Y'all have a blessed day. Please sit back and enjoy this lesson. My name is Daniel Clark, and on April 25th, I will be conducting Assignment 6 for FTT122. I will be using everyday objects to explain the following terms: trajectory, sights, gyroscopic drift, drag, the Magnus effect, the Coriolis and Evos effect, vertical angles, and transonic ballistics performance. The first of these I will cover is trajectory. Take something like a small ball and throw it gently in the air. Observe the shape of the path it takes before it lands. The ball will typically move in an upward and downward motion, causing a curved path, which is called trajectory. For sights, take something like a piece of paper, roll it up in a tube. Look through the tube at an object in the distance. This clear path, an unobstructed path, you see through the tube is known as line of sight. These are two everyday objects you can use for this. Next up, we have gyroscopic drift. It's a phenomenon that often occurs in spinning objects. For example, we can take the spinning top. On a flat surface, you can observe its stability, spinning motion, then apply gentle force to the top of the spinning top stem, pushing it sideways. In doing this, you should notice instead of moving in the direction of the force, it will move perpendicular to the applied force. This motion is due to the gyroscopic drift. Next up, we have the drag. Drag, as we know, is a force that opposes an object's motion through a fluid like air or water. It is caused by the friction and differences in the air pressure that develops as the object moves. To demonstrate this, you can take stuff like a flat sheet of paper and a crumpled up piece of paper and a paper airplane. Drop them from certain distances in the air. Observe how they fall. The flat will experience more air resistance and fall slower compared to the crumpled up ball. And the paper airplane, which are more streamlined and have less drag. These examples show that shape and orientation of an object can affect the drag it experiences. Next up, we have the Magnus effect. The Magnus effect occurs when a spinning object moves through fluid like water or air, creating a difference of pressure on either side of the object. Something that could be used for this is like a football. You can, because the spinning stabilizes as the football is in flight, but it can also cause it to curve if you throw it at a particular angle of force. Next up, we have the Coriolis effect. For this demonstration, you can use a rotating table. Place a small ball in the center of the table as it spins. Try to roll the ball in a straight line to a point on the edge of the table. The ball will appear to curve away from its intended straight path. This happens because the table is rotating, and although you aim straight, the rotation changes the ball's trajectory relative to the table. The Earth's rotation kind of acts similar to this deflection in the atmosphere, affecting weather patterns and ocean currents. Next up, we have the Tovis, correct me if I said this wrong, a Tovis effect. Example for this I will use is an airplane. Imagine you're on an airplane, which the plane is stationary. It measures in standard weight. If the plane is eastward, your weight would slightly decrease on scale because you're in rotation with the Earth. If your plane is pointed westward, your weight is facing the rotation of the Earth, it will slightly increase the weight. This is how you explain the EVO effect. Next, we have vertical angles. What are vertical angles? Angles that run opposite of each other in straight lines that intersect. For this, we can use a pair of scissors. This right here would be your EVO's point. It is called this because the two lines intersect and share common vertexes at the center, but do not share sides. Transonic ballistic performance. The last topic I'll be covering today is the transonic ballistics performance. Well, first, what is it? It is the behavior of a projectile, i.e. bullet, as it slows down at supersonic speed and approaches the speed of sound. This is a critical in a projectile's flight because it can experience significant instability due to the change in aerodynamic forces. Transonic ballistic performance. To demonstrate this, I will use a paper airplane. As a paper airplane begins to slow down, it might start to wobble and pitch up and down. This is akin to the bullet entering the transonic region around Mach 1.2 to 0.8, where it starts to experience more air resistance and shock waves that can cause instability. At this point, you are entering the transonic phase. If you ever seen a paper airplane suddenly dive or turn unpredictably as it slows down, it is sort of essentially happens to a bullet in transonic phase. The center pressure of the bullet shifts forward, increasing the likelihood of yaw and pitch, which can lead to a loss of accuracy. In real-world ballistics, bullets are designed with specific shapes and weights to minimize the transonic effects and maintain stability and accuracy as much as possible. Thanks for watching. Have a blessed day.